All right, guys, now that we know what atoms and molecules are a part of our reaction, we can go ahead and start modeling our reaction. And what I want you to focus on first is make sure you're following along with the instructions, and you might need to pause a few times to do that. But then I also want you to remember what we're modeling with our Legos represents the real life reaction that we were doing with our paper. So I want you to be following along with not just what we're doing with our Legos, but what does that mean in real life? What does that model represent? Okay. We're going to start by creating our reactants. Remember, reactants are like the ingredients to a reaction. And you're going to be making two reactants today. The first one is our potassium ferrocyanide, and that is the yellow and blue. And then the next one is that ammonium ferricitrate, which is the red and blue. Okay, and I want you to make as many of those as you can with your Legos. You can probably make around like 8 or 9, but it might not be an exact number. That's okay, but make as many as you can. And then what you're going to do, you see I've already pre-made all of mine. If you have a little beaker, which I think we'll have for you, I want you to actually put those. We're going to take them and put them in our beaker. Okay. So what this would be in real life is we'd have two liquids, and we'd have those chemicals in two liquids, and they would take those and they'd actually mix them together into a mixture. Okay. So you can go ahead and mix this around a little bit. Okay. And usually when we think of a chemical reaction, we think, oh, we add two things together and they react. But I'm going to dump this out. And what they do next is they take this and they either soak the paper in it, or they take a paintbrush and they brush it onto the paper. So I'm going to kind of try and spread this out evenly on my paper. And I want you to notice something. I want you to notice that there is not a reaction. A reaction is when molecules change. And you might notice that all of these molecules are still the same. They haven't changed at all. They haven't combined or broken apart or rearranged. So even though we mixed our molecules together, they did not react. We did not have a reaction. Okay. All right. So we're going to paint this onto our paper. So in real life, they would kind of either soak the paper in this, or they would kind of brush it on with paint. I'm just going to kind of spread mine out. And I'm going to try and make it kind of even as far as having them a little, mixed up together on my paper. Okay, so this would be like right now our blue piece of sandpaper that has our chemicals mixed into it. All right, next what I'm going to do is I'm going to cover up part of my paper, about like half of it. Okay, just like we covered up half of our paper when we went outside. We cut out those different designs and stencils. This isn't a very cool design. It's just covering up about half of my molecules. Okay. This part is really, really important. We're going to take this out and we're going to put it in the sunshine, just like we did with our real paper. So I want you to imagine we took this part out, and I'm actually going to write on this part, I might even draw a line to show where the light is. And this part we put in the light. And then I'm just going to hurry go back, and on my other side, I'm just going to write, oh, we put this part in the dark to remind myself, okay? In fact, I'll flip that around for you. So some of it's in the light and some of it's in the dark. Okay, so the question is, why didn't these react? I mixed these chemicals together, but they did not react with each other. And the answer is there's one thing that they're missing. They're missing kind of the energy to react with each other, or something that's going to make them actually rearrange and reconnect. And the thing that they're missing is sunshine. And I want you to remember that sunshine is a type of wave. Light is a type of wave, and waves carry energy. They move energy. And we're not going to get way into the details, but basically a wave of energy from sunshine is going to come along and hit these molecules. And what it's going to do is that it's going to kind of start making the electrons in those molecules want to move around. So you might remember in each atom there's those electrons that kind of travel around the atom, and those are going to start moving around more. And what's actually going to happen is they're going to start kind of jumping around which atom they are a part of. So some atoms might lose electrons, and some atoms might gain extra electrons. And electrons, if you kind of remember back to when we learned why do atoms react, why do atoms connect together, it's because of electrons. And so if we start changing electrons around, it's going to kind of change which atoms want to be connected together, right? Like these two were connected together because they had the right number of electrons to be kind of buddies. But if one of them loses an electron or gains an electron, they are not going to be buddies anymore. So what I want you to do next to kind of represent the start of this reaction from the sunlight is break these apart, okay? So what's going to happen is that sunshine is going to hit these atoms, and it's going to make their electrons start kind of changing around, and that's going to make them, they're not good partners anymore. Okay, they've kind of lost interest in each other. Okay, and now that these atoms are starting to break apart, they're going to reconnect with better partners, better pairs. Basically, now that they've kind of changed their electrons, it's going to change who they want to pair up with. And the one we're going to focus on is our iron atoms. Okay, our iron atoms are going to start combining together into these little double blue iron molecules. Okay, and these molecules represent that blue dye, Prussian blue, and I guess I've got this little extra iron, that's okay. That blue Prussian blue dye. Okay, and there are two important properties of Prussian blue that we're going to focus on. The first one is that Prussian blue has that really deep blue color, which makes it good for using as a dye or using as an ink. Okay, so that's one important, that color change is kind of an important part of this reaction because that's why we want that kind of rich blue color that made it so good. And the other important part is that Prussian blue is water insoluble, or another way to say that is it is not water soluble, or an even easier way to say that is it does not dissolve in water. Okay, so Prussian blue does not dissolve or wash away in water. And to represent that, you're going to use tape. You're going to tape down all of your Prussian blue molecules. All of those kind of ink molecules we're going to tape down to show that the water will not wash them away. It won't dissolve them. And we call that, meaning they're not soluble. They don't dissolve in water. Oh, that was fun. A little bell just rang in my class. Cool. Oh, cool. It's even, oh, here we go. I better wait. This is really happening in my classroom from the, I think this is our new bell system. So we're just gonna, we'll just listen to it. You can use this time to start taping your double blues to the paper. All right, I guess it's done. Play hockey. Awesome. So I want you to see what we have now. We've got, first of all, these molecules we started with over here, and you might think, oh, do I take these and start pairing them up? And the answer is no, because this section over here was covered up. It didn't get sunlight, which means that reaction did not happen. So over here, we still just have our molecules we started with. They never reacted together because they didn't have that third ingredient, that sunlight that we needed. Okay. Over here, we've got our Prussian blue that I've taped down because to represent that water's not going to wash it away. And then I've got these leftover, these are just kind of the leftover molecules from that reaction. Okay, what we'd call my other products. All right, and then what we did, and you're going to do this on your paper, to represent washing this away with water, we took it into the sink and we washed it away. And all of those molecules that could dissolve in water, they all washed away. Okay, and the only thing that was left on our paper was that deep blue color, because those are those molecules that did not wash away in the water. They don't dissolve in water. Okay, and those would be not just in the, I would have more than 5 of those. In real life, we'd have probably billions of those in there. So I'm going to kind of shade in this section of my paper to represent, okay, that color change would be all through that part of the paper that had sunshine. Okay, so we ended up with 2 different colors on my paper. Where there was sunlight and I had that reaction, we end up with this deep blue color. And then where it was dark we didn't get that reaction, and all those molecules we washed away, and it ended up being white. Okay, and in real life on our paper, if we were to see what that would look like, the sections that were in the sun turned blue, and the sections that were not in the sun stayed white. Okay, all right, that is how you are going to model this reaction with your Legos. Go ahead and use that to answer the rest of the questions, and that's it for this assignment.